In this section, we're going to be looking at some formulae called the addition formulae. This is a copy of what's given to you in the Edexcel or Pearson formula book. There's actually 6 formulae here. If you'll notice, we have sine of open brackets a plus b, but also a minus b as well. So there's 2 formulae on each line. This bit at the end here just means that if a plus or minus b was equal to pi times k plus a half, where k is an integer, then we're going to end up with a denominator of 0, which we can't have because it can't divide by 0. That's all that means. So you can sort of ignore that. It doesn't really change anything that we're going to do. Now you'll see where these formulae come from later in the chapter. For now, let's just start using them and becoming familiar with them. In this example, we need to show, using a particular formula, that sine of 15 degrees is equal to this. We've been told which formula to use, so we have to use that. If we do it another way, we won't get any marks in an exam. Up the top right hand corner here, I've copied what you get in the formula book. So here we go, sine of a minus b. So it's the minus that we want. So if we look at the formula, sine open brackets a plus or minus b. If we want the minus, then that's the symbol on the bottom. So when we get to the plus or minus over here, we want whatever symbol is on the bottom. It could have been minus or plus over here. And in fact, you'll see when we do some examples later with the cos and tan addition formulae, sometimes we do get the symbol the other way around, with the minus on top and the plus underneath. So it's the lower symbol we want. So it's going to be sine A cos B, and then take away cos A sine B. Now there are multiple ways this can be done. We could choose 2 numbers for A and B that when you subtract them give you 15 degrees. And it makes sense to use some of the common angles. For example, if we let A equal 60 degrees and we let B equal 45 degrees, then we know sine 45, cos 45 and sine 60 and cos 60, they're standard results that ideally you want to be memorizing. Yes, we can get them from the calculator, but they appear so often that we call them the common angles, and ideally you just need to know them. Another alternative, or we could let A equal 45 degrees and let B equal 30 degrees. That would also work. Of course, there are even more options, but I'm going to go with this one. Let A equal 60 degrees and B equal 45 degrees. So subbing that in, that does give me a sine of 15 degrees. So now I'm going to put it into the right hand side of the addition formula. So that's sine 60 degrees multiplied by the cosine of 45 degrees. And then we've got take away cos of A, which is 60 degrees, times sine of B, which is 45 degrees. So what I've done there is sine of A, where A is 60, cos B, B is 45, and then same over here, A is 60, B is 45. Now we know sine of 60 degrees is root 3 over 2. We know cos of 45 degrees is root 2 over 2. Cos of 60 degrees is a half, and sine of 45 degrees is root 2 over 2. Those are results you really should just know from memory. Of course, you can check them on your calculator. Make sure your calculator is in degrees mode, not radians mode. So here we've got sine of 15 degrees is root 3 times root 2, which is root 6, over 2 times 2, which is 4. Take away 1 times root 2 over 2 times 2, We've got a common denominator here already, and we're taking away two fractions, so we can put them over our common denominator, and that is the required result. Make sure you have read this example before we start working through it. Part A, we're going to find the value of cos of A take away B. So looking at the formulae, cos of A take away B. Take away is the lower symbol here. So the next time we get an option, we also want the lower symbol. It's really important here. We want to be using the plus here, and that's because we're going to be using cos of A minus B, and the minus is the symbol on the bottom. So here we also want the symbol on the bottom as well. So for part A, cos of A take away B, that's cos A, cos B, but then plus, definitely not minus, plus sine A, sine B. Next, we've been given sine A and we've been given cos B. So let's put those in. We know cos B is minus 12 over 13. I'm going to write that in front because it looks neater. So cos B is minus 12 over 13, and that is multiplied by cos A, which we don't know at the moment, plus, and then sine A, which is negative. So I'm going to turn this into a takeaway, 3/5 multiplied by sine B. So I'm in a situation where I know sine A and I need to know cos A, or I need to work out cos A. I also know cos B and I'd like to work out sine B. So there's a formula that will help us with that, one that you learn in AS maths. Sine squared A plus cos squared A is always equal to 1, so long as the angle is the same in both cases. So this will work for A, B, for anything, as long as the angles are the same. So using that, I'm going to work out, let's start with sine A, which is minus 3/5. So that's sine A. It's going to allow me to work out cos A. So rearranging this, we get cos squared A, 1 take away 9/25, which is 16/25. And now I need to square root both sides. But every time you square root both sides of an equation, you've got to stop and ask yourself, do we want the positive square root here, or the negative square root, or do we want both? Well, if you remember, we were told something about A, and earlier in the question, well, at the beginning of the question, we didn't really know what importance that had. Now we do know. A is between 180 degrees to 270 degrees. That means cos A, if we think about the graph of cos, so there's 360, there's 180, so this is 270 here. This is the cos graph. If A is between 180 and 270, that means cos A is negative. So we only want the negative square root here. Let's do a similar thing and work out sine B. So going back to the formula, sine squared of an angle plus cos squared of the same angle always equals 1. So sine B I don't know, but cos B is minus 12 over 13. And then rearranging this, so the square of minus 12 over 13 is 144 over 169. When we rearrange this equation, we get sine squared B is 25 over 169. We're going to have to square root both sides to get sine B. Once again, we're square rooting. We need to stop and figure out Is it just plus or just minus, or could it be both? Well, similarly to A, we've been told something about B. B is obtuse. So that means B is between 90 degrees and 180 degrees, not inclusive. So sine of B, we want to know, is that positive or negative? It's not going to be both. So the sine graph, there's 90, there's 180. Between 90 and 180, sine B is positive. So this time we want the positive square root. So sine B is positive 5 over 13. Now we can put those back into our expression from earlier. So now we know cos A is minus 4/5. And now I know sine B is 5 over 13. Just tidy this up, simplify your answer, and then that's part A done. So we're lucky they turn out to have a common denominator already. And we get 33 over 65. Now for part B, we want tan of A plus B. So going back to the addition formula we've been given, tan of A plus B, that's the symbol on top this time. So every time we meet an option, we want the symbol on top. Just ignore this bit at the end. So tan A plus B in the numerator, but 1 take away tan A tan B in the denominator. That's because we want tan of A plus B, and plus is the symbol on top. So in all the other cases where there's a choice, we need to choose the symbol on top. So this is tan A plus tan B in the numerator. In the denominator, 1 take away tan A tan B. Now there's more than one way of working out tan A and tan B here. I'm going to go with using sine A over cos A to get tan A, and sine B over cos B to get tan B. So sine A was minus 3/5. That's sine A. Cos A was minus 4/5. So that is tan A. That's tan A done. Now plus tan B, which is sine B, over cos B. So all of that is my numerator, tan A plus tan B, and then 1 take away, same again, tan A tan B. Well, I'm going to simplify these immediately now. So simplify tan A, that's going to be positive 3/4. And simplifying tan B, that's going to be negative 5 over 12. When you divide in fractions with the same denominator, then the denominators will always cancel. That leaves me with minus 3 over minus 4, which is positive 3 over 4. Similar with the other one, common denominator, so they will cancel, and just ends up with minus 5 over 12. All we need to now is simplify this as far as possible, and that is the answer to part B. So that's my numerator, 3 over 4 take away 5 over 12. In the denominator, 1 take away something that's going to be negative, so that I can make that positive. And then 3, I could cancel here, but I'm just going to go with 3 5s of 15 over 4 12s, which are 48. And then just fully simplify this, or you could use a calculator, whichever way you want to finish this off. And I get 16 over 64 3. Of course, that could be done by giving the two fractions in the numerator a common denominator and then taking them away and doing all simplifying work with fractions, or just put it into the calculator. Once again, make sure you've read the example before we start working through it. We're given an equation and asked to express tan x in terms of tan y. Now, it's not immediately obvious where tan x and tan y are going to come from. However, we've been given this equation, so let's start manipulating it. What's really important is with an example like this, if you sat in an exam, if you've got an example like this, you're not sure what to do, at least do something. So we've got sine of x plus y. You can use the addition formula and expand that. Similarly with cos of x minus y, use the addition formula and expand it. Just doing that gets you some marks. So sine of x plus y, the plus is the top symbol for this formula. So we want the top symbol here as well. So it's going to be a plus in both cases. When we're doing cos of x minus y, then it's the bottom symbol we want here. So it's a minus. So therefore we also want the bottom symbol here as well, which turns out to be a plus. So let's apply the formulae. Sine of x plus y is going to be sine of x plus y is going to be sine x cos y plus cos x sine y. So what I've done there is expand sine of x plus y. There's a 2 here. This is multiplied by 2. So don't make the mistake of just putting the 2 there. That's no good. The whole thing, both terms, need multiplying by 2. Let's just go back to sine of x plus y for a moment. Please do not ever make the mistake thinking that sine of x plus y is sine x plus sine y. It isn't. This formula shows us, or tells us, it isn't. Later in the chapter we will see where these formulae come from, but don't think sine of x plus y is sine x plus sine y. You might think, oh, just expand the brackets, but actually there's no multiplication going on here. For example, if we had 7 open brackets x plus y, what that means is 7 multiplied by the bracket x plus y. So everything in the bracket gets multiplied by 7. But here there is no multiplication at all. This is sine of x plus y, the sine function. We're not multiplying anything, so we can't use the properties of multiplication, where you can expand brackets like this. We can't use the properties of multiplication because there is no multiplication going on here. So now the right hand side, cos of x take away y, which is going to be cos x cos y plus sin x sin y. There we go. That is cos of x take away y. So again, we've got this 3 here. So don't make the mistake of just putting the 3 there and only timesing the first term by 3. That's wrong. The whole of that expression needs multiplying by 3, so we need brackets. What I'm going to do next is get rid of these brackets now. So we've got 2 multiplied by everything in these brackets, and then 3 multiplied by everything in those brackets. Now we have multiplication. We can do the standard properties of multiplication, expand the brackets. There we go, brackets expanded. Next I'm going to start thinking, how are we going to get tan x and tan y? Well, I'd like you to pause the video for a moment and see if you can come up with an idea. What should we do to this equation to start making tan x and tan y appear? Right, I hope you've had a little think. How can we make tan x and tan y start to appear in this equation? Well, if we divide the whole equation by cos x, then we're going to see some tan x's start to appear. Now you might have suggested something slightly different. You might have suggested cos y. That's fine as well. You might have even suggested dividing by both cos x and cos y at the same time. That would get us to the final answer the quickest, I'm going to do it step by step. I'm going to do cos x first, and then after that I'm going to divide by cos y. But feel free, if you want to, have a go at dividing by both at the same time if you want to. So pause the video now and divide the whole expression, every single term, by cos x, and simplify as well. So here's the first term. Sin x divided by cos x is always tan x. So this first term becomes 2 tan x cos y. Now again, pause the video and have a go at simplifying the second term. Right, I hope you got 2 sin y. Cos x divided by cos x is 1. So that's just 2 sin y. Hopefully you're getting the idea now. Pause the video and try and finish off the right hand side. There we go. Now let's divide the whole equation by cos y. So that's both terms in both sides of the equation. That's going to start to make tan y appear. So pause the video, have a go at doing that. Hope you got this on the left hand side. And I hope you got that on the right hand side. So we're getting close to our answer now, and our task is to express tan x in terms of tan y. Well, those are the only two things in this expression now, apart from numbers, tan x and tan y. So to express tan x in terms of tan y, so we've got to make tan x the subject of this equation. So to do that, I'm going to rearrange to get anything with tan x on one side of the equation, and those terms without tan x on the other side of the equation. So I'm going to take away 3 tan x tan y from both sides. And I'm going to take away 2 tan y from both sides. There we go, that's rearranging to get anything with tan x on one side and anything that doesn't have tan x on the other side. Pause the video and think, how are we going to get to the end, and try and get to the end. We want tan x to be the subject of this equation. Right, hopefully you've had a go at that. On the left hand side, really important that we factorize our common factor of tan x. So having done that, we can then make tan x the subject. So tan x is 3 take 2 tan y over 2 take 3 tan y. Now if you rearranged in a different way earlier, so on this step here, so getting from this line to the next line, you might have rearranged to get anything with tan x on the right hand side of the equation, in which case you've ended up with a slightly different looking answer, but it's actually still correct. So another answer you might have got is 2 tan y take away 3 in the numerator, and 3 tan y take away 2 in the denominator. So these are just equivalent fractions, because if you multiply top and bottom of this by -1, it gives you that other version, and vice versa. So either of these two versions are correct, and that is tan x in terms of tan y, written as an expression in terms of tan y. Now here we have 5 formulae called the double angle formulae. One for sine, one for tan, and then 3 versions for cos. These results really need to be memorized. You can derive them from the addition formulae, and we're going to do that in the following examples. But in an exam, you don't want to be spending time deriving these formulae every time that you use them. That's really going to slow you down. It's for that reason that we recommend these results get memorized. Another reason we recommend memorizing them is that sometimes you'll see the right hand side of these in your working out, and you might want to turn it back into a double angle. So you might see, and you're working out 2 sine A cos A, and by recognizing that, you might need to turn it into sine of 2A. So we don't always go from left to right on these identities. Sometimes we simplify by noticing we've got the right hand side in our working out, and then we can replace it with the left hand side. And if you don't memorize them, then you're not going to spot them when they appear. So in the next few examples, we're going to see where these come from. Right here, we've been told to use the expansion of sine of A plus B to show that sine of 2A will always equal 2 sine A cos A. Well, I've already written out the expansion of sine of A plus B. Have a think, how are we going to manipulate this to give us sine of 2A? Pause the video, and if you need to, have a think, how are we going to get sine of 2A from this expression? Well, I hope you realized that we need to let A and B be the same. So in other words, in this identity, A and B are both going to be A. So if we write sine of open brackets A plus A, of course that's going to be 2A. So really all I'm going to do is replace all the B's with A's. So every B in the formula has been replaced with an A. A plus A is 2A. And on the right hand side here, we've got the same expression twice. Sine A multiplied by cos A, and then just the other way around. I'm sure you know that multiplication is what we call commutative. The order doesn't matter. So for example, 3 sevens is the same as 7 threes. X times Y is the same as Y times X. So sine A multiplied by cos A is the same as cos A multiplied by sine A. These two expressions are the same. So we've got two lots of sine A cos A, and that is the double angle formula for sine of 2A. In this example, we're going to show that cos of 2A will always be the same as cos squared A, take away sine squared A, and we've been told to use an appropriate addition formula. Well, since it's cos of 2A, then we're going to use the cos addition formula. Here's a copy of what you get in the formula book. So similar to the previous example when we did sine of 2A, once again, we're going to let A and B both equal A. So I'm going to write out the addition formula that I'm going to use first of all. Cos of A plus B is always the same as cos A cos B minus sine A sine B. I'm going to mention again that cos of A plus B does not equal cos A plus cos B. It looks very tempting, but it just doesn't. If it was equal, then this equation would work for any values of A and B. However, if we can find values of A and B where the equation doesn't work, that proves it's not always true. So let's try cos of 30 degrees plus 60 degrees. Is that the same as cos A plus cos B? So does that equal cos 30 plus cos 60? Let's find out. On the left hand side, cos of 30 plus 60, that's cos of 90 degrees. Cos of 90 degrees is 0. On the right hand side, cos of 30 degrees is root 3 over 2. Cos of 60 degrees is a half. And a half plus 3 over 2 is definitely not equal to 0. These are both positive numbers. When you add them together, you can't get an answer of 0. So they're not equal, not equal. So that proves cos of A plus B does not, and that does not equal cos A plus cos B. Right, let's get back to the example. So I'm going to let A equal B, or let B equal A, whichever way around you want to write it. So that gives us cos of A plus A. So A and B are both A. So that's cos A minus sine A sine A. A plus A is 2A. You can put brackets around the 2A if you want to. You don't have to. It means the same thing. So that's cos squared A take away sine squared A. That's part A done. In part B, hence derive the alternative forms 2 cos squared A take away 1 and 1 minus 2 sine squared A. Both of those still equal cos 2A and always will because it's an identity, so it works for all values of A. Remember, none of the double angle formulae are given in the formula book. You need to know them. Yes, they can be derived from the addition formulae, however that takes time and you don't want to have to do that every time you need them. Of course, in an exam you could be asked to do what we're doing right now and showing where they come from. But if you just need to use them as part of solving an equation, for example, then you don't want to be deriving the double angle formulae. You need to know them, memorize them. Right, let's start with cos squared A take away sine squared A, because the question said hence. So I'm picking up where I finished on part A. I'm going to use an identity from AS Maths. Sine squared A plus cos squared A is always equal to 1. And I can use that to, for example, replace cos squared A with 1 minus sine squared A. So what happened there was cos squared A got to be replaced with 1 minus sine squared A. And we're collecting like terms here. 1 take away 2 lots of sine squared A. So that's one of them done. So we've done the 1 minus 2 sine squared A version in the question. We now need to get the other version, 2 cos squared A take away 1. Well, we could go back to the start and replace sine squared A with 1 minus cos squared A. Or we could continue from where we finished here and replace this sine squared A with 1 minus cos squared A. So there's two options. I'm going to continue from where I finished. So replacing this sine squared A with 1 minus cos squared A. You're welcome to go back to the start and do it the other way if you want to. Expand the brackets. Remember, we're multiplying everything in the brackets by -2. So therefore, this is a plus. And now, tidying this up, I'm going to put the 2 cos squared A first. And then I've got positive 1 take away 2, which is -1. And there we have the other version in the question. And that's everything done. In previous examples, we have derived the double angle formulae for sine 2A and cos 2A. Remember, there are 3 of them for cos 2A. We're now going to derive tan 2A, and it's a very similar process to the previous 2 examples. So please try and use those to guide you, and pause the video and have a go at this one yourself. So pause the video now and have a go. Right, hopefully you let A and B both equal the same thing. So that gives us in the numerator tan A, and we want a plus next. This plus because we're choosing the upper symbol here, so we want the upper symbol in the numerator, but then we want the upper symbol in the denominator as well. So because it's tan of A plus B, then it's going to be a plus in the numerator, but a minus in the denominator, because those are the top symbols. And then 1 minus tan A multiplied by tan A. Collect like terms in the numerator, and in the denominator 1 minus tan squared A. The only difference I'd do if I was doing this in an exam, I'd start by writing out the formula first, which is given to you in the formula book. That's this up here. You don't need to write out the bit at the end. I'd have written that out first and then replaced all the B's with A's. Okay, that's how we derive tan of 2A. Now these double angle formulae also allow us to convert an angle into its half angle, or vice versa. You're going to see examples of that in the following examples. In a question, it will not always be obvious that the double angle formulae are needed. For example, you're not always going to see sine, cos or tan of 2a or 2 theta or 2x or whatever the angle is, which is another reason why it's so important that you memorize the double angle formulae, because you'll need to spot them when they appear in a question, and then you might need to work backwards and go back to tan 2a or sine 2a or cos 2a. So really, really important. You're going to see that in the following examples. In this example, we need to rewrite the following expressions as a single trig function. So it could be sine, could be cos, could be tan, but it must be just a single one. Could be squared, could be cubed, but just a single trig function. So part A, first of all, I'm just going to copy out the question. So there we go. I've put brackets around theta over 2's just because I think it looks nicer. It doesn't change anything. As you see in the question itself, they're not necessary, but I think it makes it easier to read. You can also put them around the final theta as well if you want to. So this is 2 multiplied by sine of a half theta multiplied by cos of a half theta multiplied by cos theta. So this is a tricky one first up. Have a go though, see if you notice any patterns. See if you can make a step in the right direction of simplifying this. So please pause the video and have a go. Right, I hope you've had a real good go at that. Even if you didn't get anywhere, then the thinking process involved will have done you good. The key here is to notice a pattern. We've got 2 multiplied by sine of an angle multiplied by cos of the same angle. And that is the pattern we get for the sine of 2a formula, or for the double angle formula for sine. So here, A in this question is a half theta. So I'm going to replace 2 sine half theta cos half theta with sine of 2 lots of half theta. Because in this example, those A's, as you can see from the question, they are both half theta. So replace A with a half theta. Okay, so I've done that now. So 2 sine half theta cos half theta became sine of 2 lots of a half theta. And don't forget about the cos theta, that's already there. We can't do anything with that just yet, so just leave it where it is. So that's a step in the right direction. Let's simplify that. 2 lots of a half theta is 1 theta. So we've got sine theta cos theta. It's a little bit simpler than we started with, but still not what the question wants. It wants a single trig function. So once again, pause the video, have a go, think how can we get this down to a single trig function. So look for a pattern. Off you go, have a go. Okay, right, I hope you've had a go at that. The key here is noticing that we can use the sine 2a formula. If we halve both sides of it, then the right hand side fits the pattern we've got in the question right now. Sine of an angle times cos of the same angle. Up here, sine of an angle times cos of the same angle. That is the same as a half sine of double that angle. So that's what we're going to do. So here, A is the same as theta. So just replace A with theta, and the left hand side of the formula tells us half sine of 2a. So it's going to be half sine of 2 theta. 1/2 multiplied by sine of 2 theta. If you want to, you can put brackets around 2 theta. It doesn't change it, so you can leave them off if you want to. So that's a single trig function. That's part A done. However, please be aware, half of sine 2 theta is not, I repeat, is not sine of 1 theta. Half sine of 2 theta is not sine of 1 theta. I can prove that they're not equal just by finding a value of theta where the two sides give us different values. 30 degrees would do the job. So half sine of 2 lots of 30 degrees is that the same as sine of 30 degrees? Well, on the right hand side we get a half. On the left hand side we get a half times root 3 over 2. So that's root 3 over 4. Root 3 over 4 is definitely not the same as a half. That proves these two things are not equal. When we say that they're equal or they're the same, that means they need to be the same for all values of theta. However, because we've shown that isn't true, they're not the same for all values of theta, then that proves that half sine 2 theta is not the same as sine theta. Part B, same task, write it as a single trig function. This time we've got 1 plus cos of 4 theta. If you want to, you can put brackets around the angle. You don't have to. So 1 plus cos of 4 theta. Please pause the video, have a go, see if you can simplify this all the way down to a single trig function. Right, I hope you've had a real good go at that. Because it's cos, then I'm going to be looking at the double angle formulae for cos. There's 3 options here. 3 options, and whichever option we choose, we're going to let A equal 2 theta. Because if A is 2 theta, then we've got cos of 2 lots of A, or 2 lots of 2 theta, which is where we're going to get 4 theta from. So now we need to think which of these 3 is going to be most useful, and then replace A with 2 theta. But because we've got a 1 plus at the beginning, so 1 plus, for that reason, I'm going to choose the middle one. So choosing the middle version, replace cos of 4 theta with 2 cos squared. Remember, we're replacing A with 2 theta. I'm going to put it in brackets just because I like putting it in brackets. I think it's easier to write. And then there's a minus 1 as well. Don't forget about the minus 1. So because we had a 1 plus at the beginning and we've got a take away 1 at the end, then they disappear, leaving us with 2 cos squared of 2 theta. So that's a single trig function. It's squared as well, that's fine, but that satisfies the requirement of the question. In this example, we're given that cos x is 3/4 and x is between 180 degrees and 360 degrees. Stop and think, what do we call an angle between 180 degrees and 360 degrees? Yep, hopefully you remembered its reflex. Find the exact values, I'm just going to underline the word exact, of sine 2x and tan 2x. First up, what we're not going to do is we're not going to do inverse cos of 3/4 to get x and then substitute it into part A and part B. First reason we're not going to do that is I've tried it on the calculator and it doesn't give you an exact answer. It gives you a never-ending decimal. Well, when I say never-ending, the calculator fits on its screen as many decimals as it can, but then the decimals will continue forever after that. With exact answers, we're looking for things possibly involving surds. Sometimes they involve pi or the number e. In this case, I'm expecting to see surds in the answer. So that's one reason we're not going to do that. Another reason is when you do inverse cos of 3/4 on the calculator, it doesn't give you the reflex version for x, it gives you the acute version. Now, of course, you can sketch the cos graph and then work out the corresponding reflex angle. But even then, once you've done that, if you then substitute that into sine 2x and tan 2x, you still don't get an exact answer. So instead, we're going to use double angle formulae. Here we go, sine of 2x. So before it appears on the screen, please write down what sine 2x is the same as. Pause the video if you need to think. Okay, 2 sine x cos x. That needs to be memorized. Let's put in what we know. We know cos x is 3/4. So this is 2 multiplied by sine x multiplied by 3/4. I'm going to simplify that immediately. Actually, I shouldn't be using identity symbol now. This is only true for particular values of x. It's no longer true for all values of x. 2 lots of 3 over 4 is 3 over 2, and it's neater if I put that in front of the sine x. Now, I'd like to know what sine x is. I've got cos x, I'd like to know sine x. There was an example earlier in this section where we were in a similar situation. Think about what identity we used to get us out of this problem. So please pause the video and try and find sine x using the fact that cos x is 3/4. Okay, hopefully you remembered that we're going to use sine squared a plus cos squared a always equals 1. If you sub in what we know, cos x is 3/4, and then rearrange it to get sine squared on its own. Get sine squared x is 7 over 16. We now need to square root both sides, but as we did in that previous example, we now need to stop and think, do we want the positive square root or the negative square root, or do we want both? Remember what we've been told about x? It's a reflex angle. Think about the sine graph. What do we know about sine of reflex angles? Well, up in the top left-hand corner of the screen is a quick sketch of the sine graph, and you can see from the sine graph that sine of reflex angles negative. So we want the negative square root here. So it's going to be negative root 7 over 4. So sine x we now know is negative root 7 over 4. And let's just tidy that up. So that's negative 3 times root 7 over 2 times 4, which is 8. And there we go. That is now an exact answer. It's not rounded at all. You could, to check your answer, go back to cos x equals 3/4. And like I said earlier, we could do inverse cos of 3/4 to get x, turn it into the reflex angle if you want to. Well, you'd need to if you're checking your answer, and then do sine of 2 times that. You'll get a decimal answer, but then you can compare it with this, see if they give you the same number. If they do, then you've done the right thing. In part B, I'd like you to have a go before you watch my solution. Get tan 2x, remember what we've already worked out. Have a go finding tan 2x. Right, hopefully you've had a go at that. There's more than one way of doing this. We could either work out sine of 2x over cos of 2x. Of course, that gives us tan of 2x. That's an AS Maths identity. We worked out sine 2x in part A, which means we would have to work out cos of 2x using the double angle formula for cos 2x. Please don't think that we can use this cos x equals 3/4 and double both sides, because if you double cos x, you don't get cos of 2x. You'd get 2 lots of cos x, not cos of 2x. So we'd have to use the double angle formula to do it properly. That would work. I'm just not going to do it that way. I'm going to use the full formula for tan of 2x. Right, I'm going to use the double angle formula for tan 2x. If you did it a different way and you didn't use the double angle formula for tan 2x, take this opportunity to challenge yourself. Can you write down the double angle formula from memory? Have a go. Right, hopefully you've got in the numerator 2 tan x, in the denominator 1 minus tan squared x. Now the reason I'm doing it this way is we were given cos x in the question. We've worked out sine x, so I can divide those to get tan x, and then I'm just going to sub in to this expression here. So I'm just going to do a little bit of working out down the side here. Tan x, which is of course sine x over cos x. Sine x was negative root 7 over 4. That's what we found earlier. And cos x we were given 3/4. I'm dividing 2 fractions with the same denominator. You can do it however you want to, but whatever happens, you'll see the denominators will cancel each other out, and we end up with minus root 7 over 3. That's tan x. Not tan 2x, just tan x. So now we can put that in to replace tan x with negative root 7 over 3. Be careful in the denominator here. Tan x is negative. We want to square it, so therefore the minus needs to be inside brackets with the squared on the outside of the brackets. If you wrote it without brackets, then this is really bad, because then the minus isn't being squared, and technically neither is the denominator either, so don't write it like this. It needs to be in brackets. So simplify this. In the numerator, I've got minus 2 root 7 over 3. In the denominator, I've got 1 minus 7 over 9. This is not difficult to simplify, it's just fraction work. But the final answer you get, minus 3 root 7. It's an exact value because it's not rounded in any way. Okay, here we have an identity to prove. Tan of 2 theta, turns out, is always the same as 2 over cot theta take away tan theta. With an identity question like this one, then you can choose which side you want to work on and then do algebra to it, manipulate it until you end up with the other side. So you can either start with the left hand side, finish with the right hand side, or we could go the other way around. It's often a personal preference as to which way you want to work. I'm going to choose the left hand side to begin with. So tan of 2 theta, I'm going to write down from memory the tan 2 theta double angle formula and then manipulate it until I end up with the right hand side. So please pause the video and have a go yourself. You can go the opposite way to me if you want to, but see if you can get from one side of the identity to the other. Right, so from memory, tan of 2 theta is 2 tan theta over 1 minus tan squared theta. I'm now going to take a look at what I'm trying to get to. So this is the target, I'm trying to reach that. Look in the numerator, let's compare them. I've got the 2, but I've also got a tan theta that I don't want. So if I divided the numerator by tan theta, then the numerator would be exactly what I want it to be. And as you learned many years ago when you were learning about equivalent fractions, if you do something to the numerator of a fraction, so you times it or divide it by a certain number, you must do exactly the same to the denominator, otherwise you're changing the value of the fraction. So I'm going to divide the numerator by tan theta, and I'm going to do the same thing to the denominator as well. Another way of saying that I'm going to divide by tan theta is you could say I'm going to multiply by cot theta. It's the same thing. Dividing by tan is dividing by 1 over, sorry, let me start that again. Multiplying by cot theta is the same as dividing by tan theta, or the same as timesing by 1 over tan theta, because cot is 1 over tan. So these two things are actually the same. So it's up to you how you think about what we do for the next step. So if you haven't already, please try and complete the next step and then see where that takes us. Okay, so I've done that now, divided the top and the bottom. There's only one term in the numerator, that's tan 2 theta, but there are two terms in the denominator. One is a term and tan squared theta is the other term. They both need divided by tan theta. So this is what we've got. Now let's simplify our denominator. First term, 1 over tan theta, that's the definition of cot theta. And then in the second term, we've got a common factor of tan theta that will cancel, leaving us with tan theta. and that is the right hand side of our identity. So that proves it. That proves this identity is true. There are other ways of doing that question. That's just one possibility. Now this is a really good question. By expanding sine of 2a plus a, show that sine of 3a turns out to be 3 sine a take away 4 sine cubed a. First I want to point out a common misconception. Because sine 2a happens to be 2 sine a cos a, sometimes people jump to the conclusion that sine of 3a must be 3 sine a cos a, but that is not true. It isn't. Sine of 3a is not 3 sine a cos a. This is what it is going to be, 3 sine a take away 4 sine cubed a. It's not 3 sine a cos a. So please don't jump to that conclusion. It's a common error that we often see. So sine of 2a plus a, which is the reason we get sine of 3a. Now I'm going to apply the addition formula for sine of open brackets a plus b. And here it is. You're given this in the formula book in a slightly different version, but hopefully you're good at knowing these by now. Sine of a plus b is sine a cos b plus cos a sine b. So a is going to become 2a and b is going to become a. So just write this out again, but replace a with 2a and replace b with a. So it's sine of 2a cos a plus cos of 2a sine of a. So this means sine of 2a multiplied by cos of a plus cos of 2a multiplied by sine of a. You're welcome to put brackets around all the angles if you want to. It doesn't change anything. It's just personal preference. If you like seeing them with brackets, you can always write them like that. Now take a look at what we're trying to achieve. We're trying to achieve 3 sine a take away 4 sine cubed a. Notice the angles here are both just a. So we want to get rid of any signs of 2a. That's S-I-G-N, not S-I-N. That was a bad word to use. We want to get rid of any occurrences of 2a. We also want to get rid of any cosines as well. So quite a bit to do still. Let's start applying double angle formulae. So first up, sine of 2a, which is 2 sine a cos a. So that was sine of 2a became 2 sine a cos a. And there was a cos a already there, so don't forget that. There's only one identity for sine 2a, but there are 3 for cos 2a. So stop and think, which of the 3 should we use in this question? And then have a go at finishing off this line of working out. Just pause the video, have a go. Okay, I hope you had a chance to have a go. The best one to use here is 1 minus 2 sine squared a. Because of what we're trying to achieve, we want to get rid of any causes. So going with 1 minus 2 sine squared a is the one that doesn't have any causes. That makes sense. And don't forget about the sine a at the end. Make sure none of these bits go missing. Let's keep simplifying. So have a go at simplifying this whole line, and then, if you can, try and get to the end of the question. So pause the video, see if you can finish it off. So the first thing I've done is write cos a times cos a as cos squared a. And then I'm going to expand the brackets on the next term. There we go, brackets have been expanded. We've still got a cos, but thankfully it's a cos squared. So that makes it easy to replace using the identity sine squared x plus cos squared x is always equal to 1. I can replace cos squared a with 1 minus sine squared a, and then make sure you don't lose any terms or miscopy them from one line to the next. So I'm always looking back at the previous line, just double checking that I haven't changed anything. Because we all make silly mistakes. You've just got to be constantly looking for them. Let's expand the brackets, collect like terms, and that should do. So that's what we get from expanding the brackets. And then when you collect like terms, we get the identity in the question. We get 3 lots of sine A, take away 4 lots of sine cubed A. And that's what sine 3A is equal to for any value of A. Final example in section 5.1, we're given x equals 3 sine theta and y equals 3 take away 4 cos of 2 theta. Our task is to eliminate theta and express y in terms of x. And this is actually an example of parametric equations. You might have met those in a different chapter. You also might not, so don't worry if you haven't met them yet. That doesn't stop us from being able to do this example. But these are examples of parametric equations, x and y given in terms of a third variable, in this case theta, and we call that third variable the parameter. So we're going to eliminate theta. There's more than one way of doing this, as is often the case in maths. You might be tempted to just rearrange one of them and make theta the subject and then substitute it into the other one. Although that would work, we're not going to get a very neat answer. We're going to have inverse sines or inverse causes involved. We can get a much nicer answer if we do it a different way. So we're going to use double angle formulae because we see the cos 2 theta. So that's the first thing we should be thinking about. Maybe the double angle formulae are going to help us here. So I'm going to start with y equals 3 take away 4 cos of 2 theta and replace cos 2 theta with one of the 3 versions that you need to memorize. So stop and think, which one should we use in this question? I hope you realize that the best one to use here is 1 minus 2 sine squared theta. That's because from the other equation, x equals 3 sine theta, it's got a sine theta in there. So I can rearrange the other equation. So x divided by 3, that will equal sine theta. And then replace sine theta in what I've got here. So I've expanded the brackets, and now I'm going to replace sine theta with x over 3. And there we have it. We have expressed y in terms of x. Now a little bit of extra detail on this example, and this will help when you do study parametric equations and also functions if you haven't already. So this gives you a little bit of a head start. If we consider x equals 3 sine theta, well, we know sine of any angle has a maximum value of 1 and a minimum value of minus 1. So that means x in this particular question can only be as small as minus 3, and it can only be as big as positive 3. So x cannot take all real values here. It's restricted. It's equal to 3 times sine theta. The biggest that sine theta can be is 1. Therefore, the biggest that x can be is 3 times 1. And similarly for the lowest value that x can take. So therefore, this graph will only exist for x values between minus 3 and 3. If you've studied the functions chapter, you'll know we call this the domain. If you haven't already, then there's a head start. The set of x values that we can sub into the function is called the domain. Okay, that concludes this chapter.